Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. GATE 2022 Chemical Engineering, Previous Year Questions and Solutions, Chemical Reaction Engineering. In this video, we will discuss 2019 questions, question number 10, question number 11, question number 37, and question number 46. I would appreciate if you subscribe to the channel. It will motivate us to produce more valuable knowledge content for your career progress. So subscribe now before you forget. GATE 2019, question number 10. For isothermal reactor schemes, CSTR, ideal continuous test tank reactor, PFR, ideal plug flow reactor, for processing equimolar feed rates of D and E are shown in the figure. This figure shows the four schemes. The desired liquid phase reaction D plus E forming F with the reaction rate RF equal to K1 times CD squared times C to the power 0.3 is accompanied by the undesired side reaction D plus E forming G with reaction rate RG equal to K2 times CD to the power 0.4 times CE to the power 1.5. Each scheme is designed for the same conversion. The scheme that gives the most favorable product distribution is given in the problem is that all the four reactors are designed for the same conversion. So that is XA equal to XB equal to XC equal to XD. You are required to select the reactor scheme that gives most favorable product distribution. Two reactions, one main reaction and one side reaction are occurring in the reactor. They are parallel reactions between the same reactants. Let us analyze the two reactions in detail. The favorable product distribution means the product leaving the reactor should have more of product F, that is the main product, and less of G, that is the side product. To achieve favorable product distribution, you need to maximize the rate of main reaction and minimize the rate of side reaction. The main reaction is between the reactants D and E to form product F and proceeds at a rate given below where K1 is a rate constant, D plus E going dF with RF equal to K1 times CD squared times CE to the power 0.3. The order of the reaction with respect to D is 0.2 and the order of the reaction with respect to B is 0.3. Hence, the rate of the main reaction is stronger function of the concentration of reactant D compared to the concentration of E. The side reaction between the reactants D and E to form product G is undesirable and proceeds at a rate given below where K2 is the rate constant, D plus E forming G with RG equal to K2 times CD to the power 0.4 times CE to the power 1.5. The order of the side reaction with respect to D is 0.4 and the order of the reaction with respect to E is 1.5. Hence, the rate of the side reaction is stronger function of the concentration of reactant E compared to the concentration of D. The ratio of the rates of reaction Rf to Rg equal to K1 by K2 times Cd to the power 1.6 times Ce to the power minus 1.2. So Cd has a positive integer and Ce has a negative integer. To maximize the formation of F, you should keep the concentration of the reactant E lower and that of the D higher in the reactor at any point of time. In the scheme A and B, which are ideal CSTR and plug flow reactors respectively, the entire feed rate of D and E are introduced at the same time at the reactor inlet. Hence, the initial concentration of D and E are higher in both schemes A and B. In the scheme D, the entire feed rate E is introduced at the reactor inlet and D is fed equally at 5 locations along the length of the reactor. Hence, the concentration of E is highest at the entrance of the reactor, whereas the concentration of D is lowest at the entrance. This will lead to more side product formation as in scheme A and B. In scheme C, reactant D is fed at full rate at the reactor inlet, and E is split and fed to the reactor at 5 locations along the length of the reactor. Hence, the rate of main reaction will be faster and product F will be formed at a faster rate. The product formed will have more of F and less of G. Hence, the scheme C is the preferred scheme. So hence, the answer to the question is option C. For a first order reaction in a porous spherical catalyst pellet, the diffusional effects are most likely to lower the observed rate of reaction for option A, slow reaction in a pellet of small diameter, option B, slow reaction in a pellet of large diameter, option C, fast reaction in a pellet of small diameter, option D, fast reaction in pellet of large diameter. Before we go into the answer part, let us understand the concept first. This is an illustration of a cutout of the reactor catalyst bed. The gas stream in light blue color flows through a bed of catalyst denoted by the circle in dark blue stripes. This figure illustrates the 5-step process in the catalytic reaction. In step 1, the reacting species diffused from the bulk fluid to the catalyst surface. The step 2, the reactant gets deabsorbed on the active sites on the surface of the catalyst. The step 3, surface reaction takes place. In step 4, reaction products gets desorbed from the active site. In step 5, the products diffuse from the catalyst surface to the bulk fluid. Which particle size is better for the reaction, bigger or smaller? The larger the particle size, the more the time it takes for the reactant to go into and out of the catalyst particles. For a given catalyst volume or weight, there is a greater external surface for smaller particles than larger particles. Thus, the catalyst particle diameter has an impact on the activity of the catalyst for any reaction. Smaller pellets have high activity, hence higher production rate or smaller catalyst bed volume. How does the diffusional effects impact the observed rate of reaction? It depends on the type of reaction and the diameter of the catalyst particle involved. You have 4 options in this question to select. They are slow reaction in pellet of small diameter, slow reaction in pellet of large diameter, fast reaction in pellet of small diameter, and fast reaction in pellet of large diameter. If diffusion is slow, the diffusion rate dominates the conversion. If reaction is slow, the reaction rate dominates. In a catalyst bed of large diameter, the surface area per unit volume of the catalyst is smaller. If the reaction is diffusion controlled, the rate of reaction in pellet of large diameter will be lower because the surface area is lower, owing to which the activity will be lower. Hence, the answer is option B. GATE 2019 question number 37. Carbon monoxide reacts with hydrogen sulfide at constant temperature of 800 degree Kelvin and constant pressure of 2 bar as CO reacting with H2S to form COS and H2. The Gibbs free energy of the reaction is 22972.3 joules per mole and the universal gas constant R equal to 8.314 joules per mole Kelvin. If only 4 mole of H2S and 1 mole of CO are present, the extent of reaction at equilibrium is Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. For the given reaction between CO and H2S, the following operating data are given. The initial number of moles of H2S, 4 mole. Initial number of moles of CO, 1 mole. Temperature, 800 degree Kelvin. Pressure, 2 bar. The Gibbs free energy of the reaction is 22,972.3 joules per mole Kelvin. The reactants and products are assumed to be ideal. You are required to find out the extent of reaction, that is, the equilibrium conversion of the reactant. How do you solve this problem? The given reaction is a reversible reaction. You have to solve it in 2 steps. In step 1, find out the equilibrium constant. Step 2, from the equilibrium constant, determine the equilibrium conversion. The relationship between the equilibrium constant K and Gibbs free energy of reaction is given by the expression delta G reaction equal to minus RT ln K. Substituting the values of T and R and delta G reaction, we get ln K equal to minus 3.4538. So the K works out to 0.0316. For the reaction CO plus H2S forming COS plus H2, let the equilibrium conversion be Ne moles. So the number of moles of reactants and products at equilibrium is determined now. This table presents the reactants and products, the initial number of moles, the number of moles at equilibrium, and mole fraction of the components at equilibrium. The total number of moles of CO is 1 and that of H2S is 4. The initial number of moles of products are 0. So the total number of moles at start of the reaction is 5. As per the reaction, total number of moles remains constant. The number of moles of CO at equilibrium is 1 minus Ne, and that of H2S is 4 minus Ne. The number of moles of COS and H2 are Ne each. The mole fraction of the reactor components at equilibrium is as shown on the table. Equilibrium constant is expressed as K equal to YCOS times YH2 divided by YCO times YH2S. Substituting the value of mole fraction from the table above and simplifying, will get 0.0316 equal to Ne squared divided by 1 minus Ne times 4 minus Ne. Solving the equation by iteration, we get the equilibrium conversion Ne equal to 0.29. So the extent of reaction at equilibrium is 0.29. GATE 2019 question number 46. A first order irreversible liquid phase reaction A going to B with K equal to 0.1 per minute is carried out under isothermal steady state conditions in the following reactor arrangement comprising an ideal CSTR and two ideal PFRs. From the information in the figure, the volume of the CSTR in liters is shown in the sketch is the reactor arrangement for the problem. This question relates to sizing of reactors. This is an important question likely to be asked in any GATE exam. The same feed is split into two streams. One stream is fed to CSTR and another stream is fed to two PFR arranged in series. Let us analyze the data given and develop the method to solve the problem. The inlet feed concentration of A, Ca0 equal to 1 mole per liter. Total feed rate to reactor Fa0 is 100 liter per minute. The outlet concentration of reactant A of the two parallel schemes Ca equal to 0.5 mole per liter. Hence, the conversion X is the same for both CSTR and the combined PFR. The reactor volume of PFR1 and PFR2 are given as 40 liters and 60 liters respectively. You are required to find the size of the CSTR. Having analyzed the data, let us move on to the solution part. The PFR1 and PFR2 are arranged in series. For the case of sizing of the reactor, it can be considered as a single PFR of volume 40 plus 60 is equal to 100 liters. Now the scheme is simplified as below. The solution involves two steps. In step 1, determine how much feed is split and fed to PFR. Since the volume of PFR and conversion X is known, this can be determined. In step 2, volume of CSTR is determined, having found the feed rate to the CSTR. Step 1. Determination of the molar feed rate to the PFR. The conversion in PFR is X is equal to Ca0 minus Ca divided by Ca0. Substituting the values of Ca0 and Ca, we get X is equal to 1 minus 0.5 divided by 1 is equal to 0.5. The sizing equation for PFR is V equal to Fa0 integral 0 to x dx by minus Ra. Ra minus Ra equal to K1 times Ca. From the expression for the conversion X, we rewrite the relative equation minus Ra equal to K1 times Ca0 times 1 minus Xa. The equation for the reactor volume becomes V equal to Fa0 integral 0 to x dx divided by k1 Ca naught times 1 minus xa. Rearranging the above sizing expression, we get V equal to Fa naught divided by k1 times Ca naught integral 0 to x dx divided by 1 minus xa. On integrating the expression for volume of PFR, V becomes Fa naught divided by k1 times Ca naught into minus ln of 1 minus x. Now substitute for V is equal to 100, x is equal to 0.5, Ca naught is equal to 1, k1 is equal to 0.5. We get Fa naught equal to 14.427 liters per minute. The feed rate of A to CSTR equal to 100 minus 14.427, which works out to 85.573 liter per minute. The sizing equation for CSTR is V equal to Fa naught times x divided by minus Re. Substituting for minus Ra, we get the sizing equation for CSTR, which is V equal to Fa naught times x divided by K1 times Ca naught times 1 minus Xa. Now substitute for Fa naught equal to 85.573, x is equal to 0.5, Ca naught is equal to 1, K1 equal to 0.5. The V works out to 85.73 liter. So the answer is the volume of the CSTR is V equal to 856 liters. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.